success, and what to expect, and what the advantages and comparisons are between the two. So, yeah.
Which one is the one? That's it right there. Yep. I'll pop this in. What's that? We'll go back to this. And once you get to the second, I go through the first two. Then come up and you can load this one. The first two are in here. Okay. Here's the slide. Here's the slide advancer.
Well, it's good to be here again. This is the third time I've Okay, that's better. It's good to be here again. This is the third time I've participated in this summit. It's the second time I've been asked to present on a topic which is outside my core competency. The problem is I'm a Wall Street guy, right? And so when we talk about future, well, future is maybe next year. We tend to focus on this quarter and everything out there. We'll get there. The good thing is that we have three panelists who each have more than 25 years of experience, who holds combined well over 100 patents. So you're going to get a good feel for the topic. I would like to say just a couple general things from layman's point of view. One is, I think it's one of the primary points of this panel is to point out that while we've always been talking about these technologies as future technologies, there is product that is shipping today. So it's not just about when will MRAM or when will ReRAM replace NAND. There are applications today using this technology. Secondly, with Intel's Crosspoint announcement, I know in my world where we don't focus on the future, people have started asking questions about next generation memory technologies. So there's definitely more emphasis on where we're going forward in what's called the dumb Wall Street community. So I think that's important. I think the third point is I've always liked Gartner's hype cycle. So I think we're at the point where we're headed towards that peak of hype. Unfortunately, that means we have the trough of disillusionment ahead of us, which is not really something we want to look forward to, but you need to go through those points before you get to the time when you've got a productive industry that's seeing steady and healthy growth. And so now we're finally on that curve, I think. And so that's what I want to start off with. First, I'll introduce Rajiv Ranjan. He's the co-founder and chief technology officer at Avalanche Technology. He has more than 25 years of experience in the data storage industry and has worked in technical and management positions at Seagate, Comag, and Control Data. He was recognized by the U.S. Congress in 2005 for his leadership in science, technology, and commerce. He received his PhD in material science and engineering from Iowa State University. And finally, Rajiv has been issued more than 100 U.S. patents on hard drives, storage, and memory-related technologies. So, Rajiv, thank you.
Thanks. All right, thanks, Matt. Can you hear me in the back? All right. So let me start with another hierarchical chart, but in this case, mapping onto it is are the emerging memories. So if you look from the right side, of course, you heard about HDD and SSD, and where
pointer in? The pointer in there? Okay, yeah. And then you have a storage class memory, and then so this is roughly, if you map it, speed dropping a factor of 10. Of course, on the leftmost side, your CPU cache, which typically 5 nanosecond or lower, and then your RAM, which dominate DRAM here, and that's 10 to 100 nanosecond space, right? And then you have this whole storage class memory space, which is typically 100 nanoseconds to microseconds space. So if you look at of the emerging memories, the STMRAM, which is a version of MRAM, and that'll become clear as I explain in subsequent slides, that really maps into the high-speed portion of it. So it's where DRAM is and storage class. Looking at the PCM, it's been around for a while, and there were some products, and now we believe that's coming into the cross point. So that covers more storage class, part of maybe SSD, high capacity, and resistive RAM, again, more of a storage class, plus perhaps in the 3D stacking, going after the 3D NAND, right? So takeaways, STMRAM is really the high speed covering a large space there. If you go more specifically on the pain points and different areas in SRAM, you can argue, it's just sub 20 or where there's some FinFET based SRAM, but the problem there still is these are volatile, right? And as the applications are growing, more size of L2 and L3 is increasing. And STMRAM, because of endurance, so this is one takeaway, this is the only emerging NVM with unlimited endurance. So it fits in perfect for any memory application, especially SRAM and DRAM. So that's a leading candidate here, and that will fit in anywhere, any SoCs, and more specifically for IoT application, where again you need low-cost devices with NVM on there, and you have the power requirement. Going next is a DRAM, and you have 20 nanometer DRAMs coming, and as well as eDRAM in many products. STMRAM is a leading candidate for that, purely from performance, but you also get non-volatility with that, right? Of course, our challenge is to make sure we get the cost down, and there are paths to get the cost down. And the third area is a NOR flash, even primarily because mobile application is not going away. I mean, if you look at it's flat, it's staying $2-3 billion market. And there, again, I'll show you one of our products which we are sampling is going after that market with some key attributes. As a company, so who are Avalanche? We are a small company here in Valley, just a little bit, 5 miles north of you, our headquarters in Fremont. We set out, many years ago, looking at developing technology to make STMRAM both for embedded and standalone application. And very early on, we focused more on PMTJ, which I'll talk about. So our current products, which we are sampling, these are switching at 50 nanoseconds, currents below 100 microamp, 32 to 64 megabit. And at device level, these things are switching at 2 nanoseconds. So those are going subsequent products. By focusing on the product for PMTJ and the application, we have a very extensive IP, which focus all the way through MTJ, on the processing part of it, as well as applications such as in the storage area and mobile applications. Currently, we are focusing on storage and telecom sector, going after consumer after that. Our initial focus has always been on 300, so these are well suited for high volume fab. Next focus, of course, is in the gigabit size space. A little bit just educational. So MRAM has been around for the products in the market for many years. Early products were what's called in-plane, where moment used to be in-plane, and that was elongated. We focused 5 years ago on PMTJ, and that technology is scalable. In-plane was not, and it's scalable below 1 nanometer space. And just simple cartoon, you have a fixed layer, a free layer, and when these are parallel, there's a low resistance state with an anti-parallel high resistance state. So and this is what we're putting a first product. This has, these are switching at nanosecond speeds and stable at 400 degrees C. So you have to, these stacks have to be compatible with the back-end process when you put multiple metal layers. So you should be able to sustain, and our MTJ does that. So key part of the technology is how you grow this. There's very fantastic material science goes in there, although you do in one equipment, but multiple layers. And other takeaway is this is the one NVM with unlimited endurance, at device level, but of course you can't test at that. So there are TDDB models, we can extend it, and it clearly shows that. And this is pretty well accepted. And on top of that, these are rad hard. So as cosmic ray, that issue with SRAM, software propagation, we don't see that. And these are clearly extendable to sub 1x nanometer. Other key part of the technology is how you etch these. So shown here is MTJ between two metal. In this case, it's between a contact and a metal. And this is from our product, which we are sampling, one of the products. And this, you can put in any metal layers. It could be metal 2, metal 3. For embedded application, it could be the last metals, wherever it fits in. And these are pretty well stable, established. Other part is, which we found was part of the key integration is how close can you bring in. And that's where the density comes in. As you go to higher density, at the end of the day, it's a cost issue. And how close can you bring them, right? So that's that key part of development, and we have got a few IP in that space. Talk a little bit about the products we're sampling. We have two products. One is the SPI NOR, is pin-to-pin compatible, and there our key differentiator or value add is the write speed. So we are 10 times higher than the write speed and substantially higher endurance. So the number of applications where you want to back up the data, and because of the size and the time limitation, people are using multiple NOR devices. So that's the market we are going after. So that would be in storage applications and many mobile applications as a backup. Other one is the NVRAM. These are first samples both of these we have been sampling. And again, here, the write speed is even higher. It's 10 times higher. It's something like 50 megabyte per second, which is the highest write speed NVRAM you can get out there. And again, and very high endurance, low power, and these are being targeted for IoT application, automobile, digital consumer application, smart meters, and such like that. Other areas, embedded application, and there are we envision is if you look at any SoC or CPU or for that matter, IoT devices, you have memory, and as application requires a lot more memory close to the logic, right? And you have different kinds. We envision that eventually that will be all replaced by STMRAM. And one of the key reasons is this is the only NVM which switches a low voltage. So voltages are comparable to what you will have a transistor. So you don't require any special transistor. You do the logic one portion, leave the other portion aside, and you can put the memory right there. Of course, this is ultimate. Initially, we believe we'll go after NVRAM flash, eFlash, and there. And the key attribute there is going to be low power, high speed, and endurance, right? A little bit looking forward where we where we think we're going. So initially, right now, most of these are 1T, SLC, 1T, 1MTJ. Depending whether it's standalone, you're talking 6F square. If it's embedded application where you're more limited by the design rule of the logic, it'll be higher. And then subsequently, 4 straight MLC. So there are 2 MTJs stacked on that. It'll be a little bit slower, but it'll get higher density. And future, we believe, is in this, and this more like a cross point. So, although there is, we're still trying to guess, our guess is the cross point from Intel, they're using a selector from PCM, and the storage device is PCM2. So if the storage device, so while the selector switches at 10 nanoseconds, your PCM cannot, right? And that's what limits the speed, and hence, you have the issue with. we envision looking at, and there are selectors out there, there are many selectors out there which you can match with MTJ, and MTJ switches 10 nanoseconds. So, I want to leave you with this thought that eventually you will see that selector with MTJ, and these devices will switch in 10 nanoseconds, because that's how the the MTJs work. So that's where we think is future, many years out. So that's food for thought. I think with that, I'm going to stop. And I guess we wait for the question at the end, or?
We'll do the questions at the end.
No? Or end?
Yeah. Thanks, Chief. So next up, we have Joe Hare. Joe's leading the product marketing effort at Everspin, bringing new MRAM solutions to the market with an emphasis on accelerating data storage. Joe's career has been in the semiconductor industry with an emphasis on the storage industry. He worked in TI's dynamic RAM business in a variety of technical, marketing, and management positions, and later assumed marketing responsibility for TI's memory product line, including DRAM and flash EEPROM. Joe then led TI's hard drive business unit, developing and producing products for the hard drive industry. At Agere, Joe ran the storage division, bringing complete integrated chipsets to the hard drive OEMs. Joe, thank you.
Well, thank you very much. It's great to be back here. I noticed the title of our panel here is Emerging Embedded Memory, and that covers a lot. But the message I want to leave with you today is that, from our perspective, is that MRAM has really gone beyond the emerging stage to a stage where it has become in itself a very viable mainstream memory. And with that, I'll show you how we've gotten there. Just a page down is. First, just a little bit about our company here. We are the company that today is delivering MRAM, and we're delivering that in high volume. We're a private company, spun out of Freescale a few years ago. We are delivering our first generation products and have been doing so for over 7 years with over 50 million units shipped. Well, maybe in DRAM and NAND terms, that's not really high volume, but I think it does classify us as having emerged. But really where the focus is and where the excitement is and what's going to be happening next is the second generation product, as Rajiv has explained very well from a technology perspective, the spin torque, or STT. This is where we see some really exciting growth ahead. We have partnered with GlobalFoundries to bring this to production with 300 millimeter fab capability. So what do we have been doing with our technology here? It's what we are doing with spin torque is building what we're calling a persistent DRAM. It's basically got a DDR3 and then going to a DDR4 interface with a little bit of latency differences between us and a standard DRAM. But with that, we can plug into existing systems. We can build hardware and test things out very quickly, and we have done so. We've built some small drives with spin torque DRAM, MRAM, acting as persistent DRAM, and getting these kinds of performance metrics here. And as you already have seen this chart a few times today, we do believe that the difference that you have with spin torque MRAM is the ability to get down to the speeds where you start then are matching that of CPU and standard memory channels. The other thing I want to point out is what we're talking about here in terms of performance is write time, not just read. And that's really where we draw a distinction in that for MRAM, like DRAM, reads and writes are symmetrical and happen at the same rate. And as we look at 4K block write times here, with conventional PCIe and NVMe interfaces here, going down the path to where we can get to, as was pointed out really in the first talk today, the intrinsic capability and the low latency of the memory media, in this case spin torque MRAM itself, is far below what you can achieve with the interfaces. But even with those interfaces, we've got 4K blocks getting stored in under 100 nanoseconds, and that's with writing. So does this lead to a new storage tier? Perhaps it does. But we see that it fits into existing storage systems in many different ways, even today. And you can see here in some of the diagrams, that some of the pictures, that we've got MRAM products on DIMMs that become basically inherent non-volatile DIMM without any software or other hardware requirements. MRAM going onto small M.2 form factors, and a product like that was announced by one of our customers. And we've been a write cache in some of the industrial and high-performance NVMe SSDs already. And conceptually looking at how we move into some of the compute space, and we would do that through other conventional methods such as chip stacking and TSVs and things of that nature to get the interconnects down and take full advantage. And I don't know why there's a logo sitting right in the middle of the slides, but Rajiv, you got Avalanche stamped on every one of my slides. That's very good.
Well done, well done.
Well, yeah, exactly, yeah. Where we are today is write buffers today in enterprise storage applications. And you can do a few things. You can improve the performance of latency with the persistence being inherently there when you do the writes to the buffer. Or also look at perhaps taking more of a consumer class SSD and moving it up into an enterprise capability with an opportunity for some cost reduction. There are some new things coming, PCIe, NVMe over fabrics, and doing so without any disruptions to the CPU cache, and generating metadata storage and file system journals, persistent memory and software-defined systems where you may not have hardware RAID, and you can still use the persistent DRAM function as hardware support for that. And of course, the at-speed data logging and persistent scratch pads. So is it a new memory tier? It could be, but it's also fitting into existing applications and being accepted in some of the things that we've got going on today. Now, where does it fit in terms of both how does it fit application needs and compare to other truly emerging memory technologies? Of course, I'm going to give you a very positive spin on spin-torque MRAM here today, but I do want to say a couple things. First, I think that there's an opportunity for more than one emerging technology to be successful here. We are going to see that the needs diversify and that certain technologies are more appropriate for certain applications. And hats off to the Intel and Micron announcement for 3D XPoint and really making that breakthrough, because now you have very high capacity coming at these very good performance levels. We have some emerging technology with RRAM and CBRAM, another form of that, as well. But the distinction we can draw here, I think, is that in terms of latency, when we speak of write latencies, getting down to some very, very small numbers with spin-torque MRAM, where you still have some issues with write latencies in terms of block writes or just the media itself being a bit slower. The other is in the area of endurance. If you really want to play in the DRAM space, you have to have extremely, extremely high endurance. Now, Rajiv mentioned virtually infinite endurance, but I'm here to tell you that while we have delivered virtually infinite endurance in our first generation of products, spin-torque is a little bit different. There are some known wear-out mechanisms, and we're working through the engineering on those. And when you look at what it takes to really deliver 256 megabits to 1 gig going to even higher densities and look at the distribution, you have to talk about endurance at an error rate. So our combination of low error rates and very high endurance, we think, in what you will see in a specified product here, not quite infinite, but it does match the needs of these write caches here and these other high-speed buffers in the enterprise storage space today. And on top of that, from a capacity standpoint, many of these applications don't need the highest capacity that you get with NAND. And what you get with 3D XPoint, talking about very high capacities, the phase change and resistive memories showing the potential for exceeding NAND in terms of their capacity as well. So there will definitely be places where each of these technologies are used. What I'd like to point out here is, as you said, these kinds of applications with these kinds of endurances and this kind of bandwidth for reads and writes at DDR speeds, we think that MRAM is really the best fit there. And what can you, yeah, all right. Can I just page back up?
Oh, I like that slide a lot. Leave that one up there.
Yeah, this is the one. I think I went right to the end of the presentation. Can I just work my way back here? That was Dave's presentation. So just two more things I wanted to say about this. Truly about embedded here, and that is that as you look at what's happening from a scaling perspective here at technology nodes, typically what you've seen is embedded flash and embedded SRAM, following these tracks. And when you get down to this track here, below 28 nanometer, you're basically tracking the size of a transistor in those CMOS logic nodes, which you need for embedded memory. And that's basically what MRAM will deliver. At 28 nanometers and below, tracking the size of the transistor, so you're not really sacrificing area to use MRAM. And on top of that, you're getting the endurance and the speeds that will be able to replace easily embedded flash and also embedded SRAM. And that's why you see a lot of activity going on, and I think Dave will talk more about that. So just to wrap this up here quickly, there is production experience, there is volume production know-how, and that combined with now our partnership with GlobalFoundries, where quality and quantity are forthcoming here with 300 millimeter capability for both standalone products, embedded products coming from Global, standalone products from Everspin, and bringing value, really, more than just as memory, but certainly as persistent DRAM in these write-intensive storage applications is where we're targeted first. But the versatility that was pointed out a little bit earlier in terms of being able to both compute or store code and capture at very high rates, all in one memory chip here, or in one memory technology. And also, we're working on card-based solutions to really bring some of these technologies to bear in terms of real application benefits, and a lot of work going on there with the ecosystem to get controllers ready for the marketplace, and those are available today. So just that final note of moving MRAM into the mainstream out of the emerging realm. Thank you. You gonna get rid of it now?
Yeah.
Thanks, Joe. So next up we have Dave Eggleston. He's Vice President of Embedded Memory at GlobalFoundries, which he joined in 2015. His responsibility for the embedded volatile and non-volatile memory businesses, as well as the related strategic direction and initiatives. He's the former CEO and president of Unity Semiconductor, a RRAM industry pioneer acquired by Rambus. He's held technical executive management roles at Rambus, Micron, where he built and spearheaded the NAND Systems Engineering Org, SanDisk, and AMD. He holds over 25 patents in NAND flash and next generation ReRAM, storage system usage, and high volume manufacturing. He currently serves on the board of directors of 2 NVM startups. He received his MSEE from Santa Clara University and his BSEE from Duke. Welcome, Dave.
Thanks, Matt. That introduction was a little bit dry, but no, I'm not an analyst. I had that question today. I thought you were an analyst. And yes, I still enjoy picking on Intel. So let's have some fun today. Joe, I don't see any problem with the title of the panel here. It fits pretty well. But I do agree with one thing that Joe said, which is I want us to get out of the category of emerging, and let's just call it memory. Because that's the stage we're at. MRAM in particular is moving out of that emerging category and is in production, is being shipped. And what I'm going to talk about is how to use it. And I'm going to talk about it from a GlobalFoundries perspective. Who is GlobalFoundries? You know, it occurred to me as I put this presentation together that many of you might not know about GlobalFoundries. We are the second largest foundry. We have 18,000 employees. In 2015, we bought IBM Microelectronics business. We ship over 300,000 wafers a month, produce and ship over 300,000 a month. So memory is becoming an increasing importance to us in the business. And let's talk about technologies and how you use them. So what are you trying to accomplish with embedded memory in particular? I think there's a range of things that you're trying to achieve. And on the far left is the traditional view. It's there for code storage. And what you value most is how long you retain that data. On the far right, this is more the boundary we see in the future where you accelerate performance. SRAM has done that. The architectural changes with 3D XPoint do that. So that's where we're headed. In the middle, though, there's this interesting spot where you value efficiency. And by efficiency, I mean power and area efficiency. And this in particular is where embedded MRAM comes into play. How do you use these technologies? So that's my list of applications. And quick aside, if you are building a MechWarrior in your garage, please let me know because I want to borrow it for some sort of industry event. I think that would be a cool demo to have one walking around. Or a weaponized drone. So Scott Lewis, Scott, go ahead and raise your hand over here. He's the marketing guy from GlobalFoundries who tells me I can't do that because it might violate some laws. But I think to have a weaponized drone fly overhead and blow things up would be the most awesome demo for these technologies. So automotive has emerged, has come again. Automobiles are sexy, let's face it. I mean, how many of you guys went to CES? And that's one of the coolest things going on is automated driving. And talk about totally changing the business model for automobiles where it's an app. It's Uber, it's Lyft, and it just shows up and drives you somewhere. That's incredibly cool. Or a drone that flies you where you want to go. IoT, what does IoT mean? Well, IoT means everything from wearables to smart cities. So it's a huge, huge space. But this is the space where we see these technologies coming forth and being used first of all. And then many of you here are interested in storage and compute, and how do these technologies bring that speed, bring that performance that you want. So eFlash has been around for 20 to 30 years. It's a great technology for embedded. It does a really good job of retaining data. And it does it in a harsh environment. So that's why eFlash can still be used in the engine control system, engine compartment, 125 degrees C ambient. The profiles are nasty, temperature profiles. eFlash is going to be around for a long time, but eFlash faces a scaling problem. It's not that you can't scale it below the foundry node of 28 nanometer. It's that nobody will pay the money to do it. Because at below 28 nanometer, you move from bulk silicon to FDSOI or to FinFET. So as you change the underlying substrate, a front-end line technology no longer makes sense. Now specifically for these applications on the right, IoT where you value efficiency, and compute and storage where you value performance, that's just not going to cut it. You need to get it to advanced nodes. We have 14 nanometer FinFET in production today. How do we get a technology that will map to those advanced nodes? And we've made our selection. Our selection is MRAM. We have partnered with Everspin. We're open to partnering with other companies. And we believe that's the sort of value we can drive into these exciting spaces. Where you're going to see eMRAM first is closer to our core market of the MCU makers. We do business with 4 out of the 5 top MCU makers. I'm still working on that 5th. Maybe I'll land that 5th here in a couple months. But that's really a place you'll see it roll out first for embedded. You won't have 10 to the 18th endurance. You don't need it. It can't be used. You won't have 2 nanosecond write speed because the MCU makers can't use it. But what they do need is a back-end of line memory that integrates well with front-end of line logic. And that's what we pursue first. Later on, we bring you something that accelerates for storage and compute. And hopefully in the Q&A, we'll get into how does this map to persistent memory and what's being proposed here and is such an exciting topic. So I'll leave you with this thought. From GlobalFoundries, we're promoting this year 2 embedded memory technologies. One is eFlash, which is great for that harsh operating environment, and especially for automotive. That's a fantastic place for that technology. On the right, though, eMRAM, we bring you power and area efficiency. You no longer need those high voltage pumps. You get a much smaller macro. You get a smaller cell size. A lot of advantages to that, both in power and area. And then over time, we go for the performance and endurance and accelerate your systems. Thanks.
Thanks, Dave. So, as Dave said, he's not an analyst, and the problem is you give engineers a request for a 5-minute presentation, and you end up with longer presentations. So I've got a list of questions here, but my plan is, we've got about 10 minutes. I'm going to stick to 2, open it up to the floor so we can get some of your questions answered. So start off for the panel. You know, everyone up here is either in production or they're sampling. And I guess, can you get a bit more specific around if you have to pick 1 or 2 applications where we're going to see adoption? Can you talk to those applications where either product's being used or you see them as kind of the first point of adoption?
Yeah, I hope you're hearing me okay. But for the first applications that our spin torque MRAM is going into are in enterprise storage, and specifically SSDs. And some of our customers have already made announcements of using our product, and where it's going, and the value of it is as a very high endurance, high speed write buffer.
And as I mentioned, for embedded MRAM, the MCU market is the first place you'll see that appear. You'll be hearing more from us throughout this year as we reveal our roadmap.
Yeah, and you know, adding to that is other areas, telecom and consumer, special mobile handsets because of power advantage and speed. So that's another area.